Hello, everyone. Welcome to the session here. Welcome back from lunch. My name is Eric Bennett. I am the Senior Development Manager for a team called Amazon Imaging Sciences. What is Amazon Imaging Sciences? Specifically, we're a team that thinks about what our customers are going to want to have in visual content for the products that they're interested in buying, but thinking about that on a 3 to 5 year horizon. And this brings up all sorts of interesting problems and challenges as to how to think about solving these really big, gnarly issues. And the one that I want to talk to you about... Did the audio just cut out? We back? Okay. The thing that I want to talk to you about today is scaling photorealistic 3D content creation, and specifically doing that with machine learning. This is a hugely difficult problem. And what I'm going to be talking about today is a framework for thinking about how to solve this problem. What we're going to go through is first a discussion of what I call the rules. These are the ideas of what have made product imagery for the past century, and why I believe that due to changes and evolution that's occurring due to 3D content, that these no longer apply. Then I'll talk some about how 3D is impacting retail, and then specifically what it is I mean when I'm talking about 3D, so that we're all on an even playing field as far as the content that we have. Once we think about that, we can think about where does this content come from? And it can come from a variety of sources, all of which are problematic in one form or another. And then this leads to the inevitable question. How in the world do we make this scale? How do we make it scale so that we could achieve this state perhaps sometime way in the future where every product someone might want to buy or find on Amazon has a photorealistic 3D model associated with it? And then we're going to wrap up and think about some of the big ideas from the talk. So let me begin. And I want to motivate this by talking about these rules and why I think they no longer apply. Basically, everything that we have and that we know about what makes good product imagery has really been defined by a century of paper catalogs. I mean, if you think about it, what is it that we're doing? We're thinking about putting images onto a page. It's just a very different kind of page than it was perhaps 100 years ago. And as a result, commercial photo studios are ostensibly doing the same thing that they were decades ago. It's a very simple thing, that you want to create a few representative images and then have some descriptive text. Except this is a hugely difficult problem. Because the question is, what are those good images? What is it that you might actually want to show if you only have the opportunity to show a few different images to a customer? And so you want them to be the best. You want them to be the most educational. You want them to be the most well thought through. And therefore, there have been rules and things that people learn over time or expect to have in those images in order to provide a good customer experience. But I ask, is this really a good customer experience for the year that we live in? Things have changed so much, and yet we're influenced so much by the past. I think it's time to reconsider some of these notions. I would also challenge that there even exists the idea of an idealized good image, because what's a good image for you might be a bad image for you. And this idea of how do we think about personalization is a deeply customer-centric idea. Now, this concept that we're essentially already thinking we know what a good image looks like is actually informed by what has happened a long time ago. And a good example is this image here, taken from a catalog over 100 years ago. And we can see that although it may not be a photograph, it actually represents many of the same notions that we expect to have from imagery on a website today. Not only is the styling very similar, obviously the fashion is very different than what we would find today, but if you look at things like the way in which the model is holding her feet, it actually isn't that different from what we would find in an image today. So have we really learned all that much, or are we continuing to repeat things because it's what we've seen before, and therefore expect that it's what we want to see in the future? And again, this is a paper catalog. It's not a website. It's not an interactive experience. In fact, I can push this even further and say that if I show you an image like this, it's actually very hard to tell when this image was taken. Was it taken 30 years ago? Was it taken last week? the way in which the model is posed, the way in which the fabric is styled, all of these things are very similar to what we have today. So obviously it's not going to surprise you that this actually is just an image from Amazon that applied some Photoshop effects to. Again, nothing's really changed, but by the same token, these are very difficult things to do, and this is a well-honed craft that people spend many, many years learning how to do. Is it going to serve us for the future, though? That's the question I ask. And underneath all of this is this notion that it's very expensive to take photographs. And so you only take the photographs that are targeted towards the experience that you want to have on the back end. But immersive experiences don't work that way. And so when we think about 3D content, we think about opening up that realm of immersive experiences that run the gamut, that I'll talk about in a moment, but that no longer have this one-to-one correspondence of there's an image that we took at some point in the past that may have taken a fair amount of money to do and an experience on the back end. Instead, there's this many-to-many relationship, and I believe 3D is at the heart of that. So hopefully you pick up on the point that I have, that 3D is disrupting retail in both subtle and obvious ways. And it was ripe for disruption because this change hadn't been happening. And now when we think about 3D, we have to think about it in terms that are very obviously 3D, things that are in your face. This is a 3D experience, and we want you to know it's a 3D experience. But also things where that's not the case. And one of those things right off the bat is the detail page. This is the modern equivalent of that paper catalog we talked about before. And why not use 3D imagery for this? This is a 3D rendered image that's up on Amazon right now of this chair. We didn't even need to have physical access to this product in order to be able to create a 3D model from which we could create this content. And therefore, it enables us to essentially light it any way we want, to pose it any way we want, and to change it in the future at very minimal cost. So even though it's a 2D experience, it uses the 3D content. But once you have this, the opportunities open up. A 360-degree spin is one obvious thing that, again, fits into the general context of what we expect to be an Amazon-style online shopping experience. But again, jumping further, what about interactive shopping? What if you wanted to redecorate a room? And I'm going to be showing some experiences that partner teams to ours at Amazon, the home team and the A9 team, have put a tremendous amount of effort into making, and I'm happy to show them. That specifically in this case, you have the opportunity to swap furniture in and out, and to have the light and reflectivity inside of that scene properly reflect the furniture as you swap it in and out. Again, utilizing the exact same underlying assets. And of course, one of the ones which is most forward-looking and prevalent is augmented reality. The ability in order to put that exact same 3D asset, again, into a scene and to be able to manipulate it in order to configure it and to be able to really see in situ what the product is going to look like. The magic of this happens when you make the model correctly, and it's done in a way that enables you to not have to change it for each of these underlying experiences. And that's actually easy, or it's much harder than it sounds, because in order to make it work in augmented reality, it needs to have very specific constraints that work for a mobile phone experience, which is far less powerful than the other experiences we have. So we actually have to think about all those things up front before we start thinking about 3D content. But at the end of the day, Amazon is a customer-obsessed company. And 3D, in my mind, lets us put customers first, because there is no one-size-fits-best experience or imagery or any of those things for any particular customer. We want to think about all the experiences customers might want to have and create generalizable content that works across all of them. And I will say that single-use photography does not work for interactivity, and we literally tried to make it work. That experience I showed before, the showroom where you were able to swap furniture in and out, we really tried to make it work using photography because that's what we were good at. That's what we have. And it ends up that it just doesn't scale to that. So we have to make this jump. It may be a hard and difficult jump, but it's one that we need to make. Okay, so if you're going to do this, what are the limiting factors? I believe it comes down to two things. The first is, what is it that you can actually make photorealistic? And renderers are getting better and better, technology is improving, but at the end of the day, if it doesn't look real to the customer, it doesn't deliver a customer promise of what you see is what you get. So whenever we use 3D imagery, it must meet that bar. And for certain things, like I'll talk a lot about furniture today, that's something which is, it has many properties that enable it to be good for photorealism, but not necessarily other product lines that are much more difficult that I'll talk about later. And then the big question comes up of how much of that content can you actually get? Are you just going to have like a handful of content? Or are you going to have a wealth of it that actually leads to immersive experiences that customers want? And yes, I'm going to talk a lot about furniture, and I already have, but I don't want this just to be about that. Let's take this case. This is a very specific beauty cosmetics type case. And as we look at this, we see that this is a completely different styling than we saw for anything having to do with furniture. And also, it introduces all sorts of other challenges in properly rendering this. Specifically, those little plastic caps on the top there, very difficult in order to do. But at the end of the day, it's nothing compared to the bigger challenge of how in the world do you actually present this, and what underlying content do you actually want to have? Is it this? Or is it this? This is actually the way you might see it displayed if you walk into a department store, for instance. Which one of these two is right? And do I need to generate 3D content for both of these in order to be able to open up the experiences that we want to have, the breadth of them? So what I will say is that although I'm talking a lot about one case here today, there's very interesting, unique challenges that change very much depending on what type of thing you're looking at. So hopefully by now I've motivated the problem, and I want to now spend a little bit of time talking about what it is that I mean when I talk about 3D. And for some of you, this will be a review of things that are well known, but I want to make sure that some of the concepts I talk about later on in the presentation are well established. And the first thing that I want to talk about is, I keep using this term, this very vague term, 3D. It's 3D this and 3D that. What exactly am I talking about? I'm talking about two very specific intertwined ideas. It's about content, and it's also about experience. And if you put a bunch of engineers together, which for me is fantastic, and you talk about 3D, they start to talk about what are the great experiences that you could build. I could build an immersive experience to do this. I could build photorealistic content in this particular setting. I could show the content from many different angles. I could make it interactive. I could do all these things. I can make it run on mobile, on desktop, AR, VR, video games, all these various things. This is what you think about. But I also think about it as a very difficult technical challenge, but also in some ways a shell. The engineering effort in order to go into building an experience really isn't that different if it hosts one piece of content in it or a million pieces of content. It's kind of a sunk cost, if you will. It's very difficult, it's an ongoing challenge, but it really doesn't matter so much for the experience itself how much content goes into it. And so the less immediately obvious challenge, whenever you build an immersive experience or something that utilizes this, is it just going to be a few things that you get to do and then that's it and it's more of a toy? Or is it actually something that is going to be a rich experience? And if that happens, how in the world are you going to populate it? So I'm always clear up front that when I talk about 3D, I'm disambiguating those two ideas. They're both very difficult. But at the end of the day, if you really want to have a large catalog of content inside of an experience, it will eventually dwarf the amount of work that you have to do in order to build the experience. When I'm talking about 3D models, I'm really talking about two things. And again, I'm just breaking this down so that we're all on the same page here. The first thing is that there's geometry associated with it. This is our 3D geometry, most commonly represented using flat polygons, sometimes triangles. And And this is something that approximates a teapot in this case, but it's got kind of boxy lines. So the first thing you do is, if you want to make it look like it's smooth, like it would be in real life, you add more and more of these things. However, now I've introduced a challenge. The challenge is that I've made this much denser. I've made it much more data that needs to be transmitted if I wanted to build a mobile experience. That's not necessarily good. And if I hired an artist to go edit this content, that the representation in the middle is actually really bad. Now there's a whole bunch more things you have to manipulate, so many more things that you have to edit. So that's not very good either. So we start thinking about other representations and how content might be better edited. And we get into things like patches, curved surfaces, things that you see on the right, which are much more friendly to artists, but are not necessarily good for rendering. So we look at all of this content, and although this is kind of a toy example here, it becomes much more problematic when we think about other content sources that are not things that were originally created as 3D content for computer interactive display. The second thing is materials. So without materials, obviously everything's just going to be this kind of white color that we don't really have any idea what the material is. So we have to spend a tremendous amount of effort as well into figuring out what the material is. And this is a space where there's been tremendous innovation in physically based materials over the past few years, both in terms of their rendering and in their creation. And it enables us, in order to go from that into a much more realistic model. And then one of the things lurking in the background, I'm not going to talk a whole lot about today, but is how those materials are actually stored in the form of a 2D texture map, and more specifically, how those correspondences are made between the 2D texture map and the model, which is typically referred to as the UV map of the product. This is something which is another skill in and of itself to create and to do efficiently. So these things, the geometry, the materials, the UV map, all of these things need to be in place in order to say we actually succeeded, we were able to create something, which is, at the end of the day, what we're after. And lastly, it's about rendering. This is getting back to that experience notion. That the way in which we render content is very different depending on the modality in which it's being displayed. The constraints of a 60 frame per second augmented reality mobile device experience are very different from what we might have for a 10+ minute offline render on a super high power machine like you see on the right here. So we need to think about both of these. And as I said, and I'm going to reiterate this point because I think it's something that gets missed, is that if you don't build your content right in the first place, you don't have the ability in order to instantly drop it into the next experience. And that ends up being something that is not what you want to have, because you didn't really get the benefit. Okay, so this is the motivation. Let's start thinking about where this content really comes from. The first thing, and the thing that I'm going to dive into in a moment, is if you want to have 3D content, one thing that you can do is you can have it handcrafted by 3D artists. This is the idea of taking a set of images, hopefully representative images, often in the order of, let's say, 5, and saying, here's the dimensions of the product, and here's some pictures. Go and make a 3D model. And it ends up that this actually works really well, and the results are surprisingly good. Or maybe not surprisingly good. There's a lot of skill and a lot of craft that goes into making these, and they have wonderful properties. They have wonderful editability, they have wonderful topological properties. There's so many things about them that are good. The problem is, as I'll show in a moment, they take a really long time to make, and therefore it flies right in the face of thinking about how in the world we would have a 3D model for everything inside of the Amazon catalog. So you think, okay, if we don't want to make the content from scratch, then one other thing that we could do is we could go and get the original CAD CAM drawings of the content and say, can we find a way to convert it and to bring it into a similar system? And this is a whole nother set of challenges. It's very difficult in order to be able to do this as well because the representations are very different. For example, as I talked about before, when it comes to the geometry that we find from artists, it often comes in the form of patches. It comes in the form of things that are very different. In this case, for a lot of CAD/CAM, it comes in the form of rules. Shapes are defined more by rules than they are by explicit polygonal representations. And so there's a great deal of work that needs to happen, and there are a very large number of different descriptions as well as to how that content might be. So this is a problem in and of itself. You could think about another representation, such as fabric and textile patterns. This would make sense if you wanted to do things like you wanted to have pillows, you wanted to do upholstery, you wanted to do clothing. But again, this is a whole other set of problems that come up because these representations are entirely different from the way in which you think about things. They're often 2D representations that need to be abstracted into 3D. The example I always think about is a pillow. If you look at the pattern for a pillow, it's going to be kind of a flat two-dimensional square or rectangle. It's not what it is in real life because there's actually this added process. There's the stuffing that goes into it. And when you think about that, you then think about challenges such as physics simulation. The same thing goes with like a dress. If I were to take the pattern of a dress and attempt to put it onto a model or make it into a model, I have to think about things like physics simulation as well. So this is a challenge. It's not an easily solved one, and it's out there. The last thing, and this is great if you have physical access to the product, is let's scan it. And there are a number of wonderful photogrammetry techniques for doing this, and I'll talk about some of them later. But essentially, if you have a device or a mechanism in order to be able to take many images and other sensor readings off of the product and to be able to run it through what's called a reconstruction pipeline, that you can recreate 3D content. But it's got its own problems too. For instance, it usually requires some form of cleanup. And it really only works super well on things that are diffuse in nature. So you get things that are really shiny, really transparent, and translucent. These have problems there as well. So this isn't a solved problem either. So we kind of go back to where we started. How do we do this problem well? And we do it well with artists. And as I said, artists plus images equal great results. We know that if we have highly skilled artists who have spent years building 3D models and we give them a set of images, that the results are pretty much exactly what we're looking for. So that's great. As I said, the problem is that it takes a long time. But it's also, to me, astonishing what can be accomplished with so little information. All they had was a couple images and some dimensions, and yet they were able to make something which is inordinately complex. And that to me is inspiring, and in fact it kind of inspires this whole notion of this problem space, that they're able to do this and to be able to do it well. How? How is that possible? And they're going to go and they're going to spend some guesswork in order to help make this happen. But if you look at a 3D model that's created and compare it against the actual physical object, even if it was only just from photographs, they were able to do so with far less ambiguity than you might actually think. Looking at this exact same example, zooming in on it, you see that there are all these fine details. There are notions of piping around the edge of the chair. There's top stitching alongside the edge of the corner there. The joinery that exists for the legs of the chair, and the materials that exist that have a great deal of fine detail in them. These are all things that are created with very little information, and yet they end up being surprisingly correct most of the time. So, as I say, I'm inspired by this. Now, just to kind of show you the level of challenge that goes into building one of these models, I'd like to show a short video of the process of creating one of these at Amazon. So what you're going to see here is, again, this chair, which you've been seeing for a while. And the first thing that we do is we think about modeling the product. And the artists are going to do this using a variety of techniques, often working directly with the geometry, but also other things such as subdivision surfaces that enable them to be more efficient in how they do this. You can see how minor edits are made, small tweaks. Once the geometry is in place, then the creation of this UV map, this 2D representation for material generation is created again by hand. This is massively sped up. In order to do this accurately, it takes a long time. And then you also saw that they were able to use some symmetry, which I'll talk about later, in order to replicate certain elements of the product. Now, the tools that exist for things like physically based material generation are in my mind, astonishing. And we can watch here the artists try and match this from an image. And then they drop it into a system that actually replicates Amazon's physical photography studios. So all of the rules and guidelines that exist for how 3D content or how photography happens in the studio is actually transferred into the 3D world. So we can apply programmatic logic to things like lighting in order to maintain consistency for the user experience, even for an artist who's never created an Amazon product before in their life. And then lastly, as you saw here, that once you have that 3D model, the other benefit I really haven't talked about yet is the ability in order to put different materials on it, which is an incredibly difficult process in real life, but it's very easy in the virtual world. Okay, so I've talked about why it's important. I've talked about why it's difficult. Now let's think about how we go about solving this problem, because it's not immediately obvious how to go attack this problem. I want to figure out how to make a computer be able to do essentially what that artist was just showing working on. How in the world do I go after that? How can I have them go from images to, or have that machine go from images to a 3D model? And if you talk to people, the starting place seems fairly well established, and it's essentially computer vision. You would say, man, this sounds like a computer vision problem. I have images, and I want to make a 3D model of it. And so I want to talk here about a little bit of how this works. Again, it's a review for many folks, but I want to talk about this because I want to talk about why it fails. So essentially, if I was to use computer vision, and more specifically I'm talking about the subfield of 3D reconstruction, going from, in this case, images to a 3D model. Let's say I wanted to make a 3D model of a shape in space. And we're going to have my kind of hand-drawn images here, just to kind of illustrate this like a chalkboard. So if I want to make this, this 3D model, essentially I don't have physical access, or I don't have the computer being able to access it. So what do I have instead? I have a photo. So I take a photo of that product, and I say, I want to reconstruct this, this 3D model of it. So I think about it, and I say, okay, well, the photo must have been taken from an eye or a camera that was somewhere over here in relation to where I think the object was in space. And now I want to go figure out how to reconstruct this. So essentially what I do is I think about a point on that image, a pixel, and I say, where exactly is that? Where is that pixel, not just in 2D space, but in 3D space? So I do this whole process of drawing a ray from where I think the camera was through the image into the real world, and I say, bam, this is exactly where that cube is, and that's exactly where this pixel is on it. I know where that 3D point is. Except you don't, because if you've ever taken a drawing class, you know that you don't actually know that information, because it might as well just be something that's larger that's further away. It's an ambiguous problem. It's under-constrained. So instead, we have to rethink how we do this. So the one image is simply not enough information. So you back up and say, okay, well, then let's take another image, and let's figure out where that camera was, and let's figure out what the relationship was between the original two images and the original two viewpoints. And then let's try and find the exact same pixel in both of those images. They're going to appear in different places. And if I can do all of those things accurately, I can then draw a line back into space. And I now have two intersecting rays in space, and magically now I have a single 3D point. I went through all that work to get a single 3D point in space. So this is good, except it's incredibly noisy and difficult to do because all of those processes that I talked about, each one of them introduces more error. Now, if 2 cameras was good, you could say, okay, I want to have even more. I want to have 3, I want to have 4, I want to have 5. And this does introduce more error into the problem space, but it still doesn't solve some key problems like only the things that were clearly on a corner of the object or in a high texture region can be clearly reconstructed. So this doesn't work terribly well either. And if you noticed, if that was the case, I just used up all of my 3 or 4 images. And I just said that one of the key problems I wanted to solve was how in the world we make a 3D model with only a few images. If I take them all of the front side of a product, I have no information about the back of it or the side of it or any of those things. So I've already lost. Now, there are other things you can do. You can start thinking about introducing texture into the scene by projecting images onto the product. But then I've disturbed the scene. And I would call this kind of diminishing returns, and it's very hard to replicate. Essentially, in order to make this work, you need a very large number of cameras, and you need laboratory conditions with extreme precision to be able to do this well. And that's pretty much exactly what I don't have in order to solve this problem. I have a set of images that I probably didn't even take myself that have none of these constraints applied to them. And even if I was able to do all of these things, the results are still inferior to what I would have gotten if I'd given it to an artist. Because I don't get the geometry that I wanted to have. I don't have that nice editability. I don't have the topology that I wanted to have. So this is very problematic. So basically, my thesis here is that computer vision in and of itself is not going to solve this problem of what I would call sparse image reconstruction. And I believe that's because at the end of the day, classical computer vision is predicated upon its generality. That computer vision algorithms don't know a house from a chair or a chair from a person. There's none of that information. The example I just gave was very much about how we looked at a single point in space, a point that was completely separate from every other point in space. And this really means that the underlying problem is almost too difficult if we want to solve it this way. And we think to ourselves, oh, we're people, we're good at solving these problems. We know exactly how we could go about, if we're smart enough, we can build algorithms in order to do this. But at the end of the day, that we're very bad at doing this ourselves. For example, if you had never seen a chair before in your life, and I only ever showed you 2 pictures of the front of it, or 3, and I said, I want you to draw for me what the back of that chair looks like, you'd probably have very little idea as to what the back of that chair is. You don't have a notion in that world of what I would call chairness. There's no notion there of what makes a chair a chair. And trying to solve this problem without that information is almost impossible. So just to further illustrate this point, I'd like to show some examples using pure computer vision in order to capture content. So again, we're going to stick with chairs here for a moment. That if I said I wanted to do this 3D reconstruction process on a chair, this is actually a small chair, what I could do is I could create those laboratory conditions I talked about before, all those things. And in this case, I'm able to create a 3D model automatically that is pretty nice, actually. It's got nice crisp edges. The lines on it are good. The material reconstruction is good. Great. If you can do this, this is wonderful. It does require, in many cases, physical access to the product and a laboratory-type environment. Again, not the problem I'm talking about solving today. So if we start to say, okay, let's cut this down. Let's take 1/3 of the input images that I show here and try doing this, maybe make it a little bit more realistic. We get an example that looks like this. Quickly, we see things degrade when we're down around 30 input images. The edges aren't good. The floor is creeping into the chair itself. There's bad disambiguation between the foreground and background. And when we start to approach the kind of image inputs that we would have for the problem we are trying to solve, things get really bad. For instance, here's a reconstruction of what happens where this chair seems to have reverted back into being a tree, or in this case where the chair didn't appear at all. The system didn't even know it was supposed to find a thing that looked like a chair there, and guess what? There wasn't even enough information to be able to discover that there was a 3D shape there at all. And this is on the order of magnitude of input images that we're talking about today. So computer vision in and of itself is not going to address this problem. So what is? I think it's a simple insight, and it's one that actually resonates very much with the machine learning emphasis of the Remars conference. It's talking about taking advantage of the fact that we ourselves have seen a lot of chairs in our lives. And I mean a lot of chairs. There are a lot of chairs. I've spent a lot of time thinking about this, way more than I'm, anyhow, so there are a lot of chairs in this world, but by the same token, there's a lot of trends inside of that data set. And not just, the artists have seen these chairs in their life, even before they ever come and work on a single model for the sake of 3D modeling. And this implicit idea of just knowing something is very important because it actually causes us to rethink the problem, that maybe we've made computer vision, in this case, way too difficult, and that really just understanding the context of a product or a type of product might be at the heart of solving this problem. And so really this idea of us having seen a lot of chairs, this is my key insight. Like, I'm going to talk about this and go into more detail, but really at the end of the day, this is the core underlying idea of what connects the dots. So if we have this idea of there being a world of chairs out there, the next question is how do we start to teach computers about this idea of inherent chairness, of what it is that you should expect to find when you're running your computer vision system so that you know that you're creating something, you're on the right track of creating a chair, so you don't end up in that case where it's just a blob on the floor, that actually you expected to find a chair, this is what a chair should be, what data supports this notion that we found a chair. So how do we teach a computer to do this? The first thing is we start with data. Again, this is not a big revelation for a machine learning conference. But the idea here is that the quality of the output that you expect to get for things like product reconstruction has so much to do with the quality of the input information. And this is something where I'm very excited because we're thinking already about building that corpus of 3D content that empowers both user experiences in the now, but also powers the type of machine learning techniques that we want to have, because we've seen more and more and more chairs in our world, and hopefully not just chairs, by the way, but it's something which I like talking about. So you have to build that corpus to begin with. And doing so with the photorealism in mind opens up the door later on in order to have photorealistic outputs. And so thinking about this from the Amazonian standpoint, that is something that is essential to us from day one. Photorealism in everything that we do. The next thing is we need to think about all the inherent notions of what makes a chair a chair. And this goes for any product. If you think about it long enough, you start to see patterns in what actually exists. And in the case of furniture, for instance, there's typically two patterns that keep coming up time and time again. The first one is symmetry. And this is actually one of the best tools we have at our disposal. It seems like a very basic idea. Yes, things are symmetric. But it actually opens up a whole realm of things that we can do. Because if we expect to find symmetry, we actually know that we're getting multiple samples, multiple visual samples of the same thing from within inside a scene, and that those can error correct each other. So we can think about the notion of, for instance, if the chair is symmetric down the vertical axis, then we expect that the geometry on one side is going to be the same as the other. We can use that as an input into machine learning on the front end, and we can also think about how we can have systems that can detect that and enforce it as a constraint during the reconstruction phase. Inside of that, and sometimes often combined with it, is the idea of part-based hierarchies within inside a scene. And in this case, this particular chair is broken down in the image on the right into a number of color-coded regions. Some of those have symmetry in and of themselves, but also we notice that there's a lot of patterns that exist between products that exist only on this level, not on the holistic level of the product, but somewhere in between the idea of a single vertex in the scene and the entire model. And these ideas of thinking about things in a part-based metaphor really open up the reuse that I believe is essential in order to solving this problem. Because being able to reuse content enables us to be able to capture and transfer all of the fine detail from it. And when we think about photorealism, that's actually one of the most important aspects that we have. So to frame this all up, I want to think about what is the mental model for attacking this problem. And at the end of the day, I keep coming back to this simple axis, or two axes, that I use to evaluate all of the algorithms that exist in the realm that might actually help us assist in solving this problem. And the simple solution is that this is not one size fits all, that we actually need to be looking at a whole class and family of algorithms that exist along a single line inside of this space. So let me elaborate. Specifically, the first axis I'm going to talk about here is the reconstruction versus retrieval axis. So another way of saying this is, in many ways, it's the computer vision and machine learning axis. On the far left is the problem that I detailed before, having to do with computer vision. Essentially, we had no information about the whole of the product, and we tried to essentially work from complete scratch. Only the information that we were given, we tried to come up with an answer. And on the far other side is the retrieval problem, which is to say, I've exactly seen this before, and I want to reuse it as is. So you can look at somewhere in between is essentially where we want to be. But if we have seen something exactly before, why wouldn't we want to use it exactly as it is? And on the flip side, if we know we've never seen anything before, or something we've never seen before, then why wouldn't we just reconstruct it from scratch? Because nothing else is really going to help us with that. So we need to be thinking along these lines. And then we also need to think along the classic top-down versus bottom-up granularity problem when it comes to solving machine learning. Specifically, if we think about the bottom-up approach, I'm thinking about working at the vertex level. I'm thinking about how we essentially reconstruct the model triangle by triangle. And on the top, I'm thinking about the model as a whole. I'm thinking, I want to go find this thing in my catalog as is, and there it is. It's essentially, I'm operating on every triangle in the scene at the same time. And then there's that wonderful part in the middle where I get really excited that involves those things like symmetry, that involves those things like part-level abstractions that aren't about the whole, but they are actually about the parts that we actually see replicated time and time again. And again, the ability in order to reuse them, if we can identify them, enables us to be able to do so with extremely high detail and visual clarity. So if I look at where machine learning and search sit for the most part, I see them up in this general realm, that it's typically about trying to retrieve something from a large corpus, and it's typically the object as a whole. And what I talked about earlier with multi-view computer vision reconstruction is over here. If you're thinking about this problem, I encourage you to be thinking about this line that connects these two. This is where I think the magic is. And it's about thinking about, when do we think about things on the whole? When do we think about breaking them into parts? When do we think about reconstructing them? When do we think about, wow, I have never seen that before, and I know my computer vision algorithm is going to fail. Maybe this is where I should be having an artist come in and work on that element as well, augmenting this process. We have this whole idea here of trying to break down a product into many different levels of abstraction to be able to retrieve retrieve things when we can, and to be able to reconstruct things when that doesn't work, and to be able to fuse those together into a workable solution. This is all well and good, except for the problem of this requires a great deal of data. And as I said before, what we need is photorealistic data, and we need data that is heavily labeled, and data that we have a great deal of consistency across. And this introduces a number of challenges. So the mental model that I like to have is one where we say, look, we know this is a problem, and it's something that really only time will help us overcome. So we want to think about it in a cyclic manner. We want to think about chunking the problem up into types of products and objects that we can actually go very deep on and build that corpus and continue training against it in order to see the results that we want to have. And yes, it may require that some of the tricks that we use for furniture don't necessarily apply to cosmetics. It might be easier, it might be harder, we might need to have multiple geometry variations like I spoke about before. All of these things need to happen. And then, once we've achieved that, once we're able to have the machine learning computer vision model that gets us to the quality bar that we want to have, then we're going to go back and we're going to say, okay, let's go look at a different part of the catalog. And these might be very narrow slices of the catalog. It might just be, a certain set of chairs. It might be love seats. It might be desks. It might be cosmetics, it might be televisions, it could be any of these things, but they may be very narrow, they may not be broad to begin with. But soon, over time, building this corpus and training, going and building another corpus and training against more models, this allows us to start thinking about how we attack this problem long term, until eventually we actually do have the breadth of catalog coverage that may take a very, very long time to achieve. And I know this is a difficult problem because, again, if I just look at that narrow space there of what makes a chair, and how can I teach a computer in order to do that, and this is kind of like my nightmare photo here when I think about all the things that exist out in the world. This is a tricky problem. And this is just one narrow subslice of the things that exist in the Amazon catalog. But I love a good challenge, and that's why I'm so excited about trying to figure out what are those set of algorithms that exist that enable us in order to attack them. And as I say, I think they exist along that blue line. The question is, how do we get there? So with that, I want to wrap up with some of the key takeaways from the talk. The first one is this, where we started. It is 3D is transforming retail. And I believe it leads to deeply personalized experiences, very customer-first experiences that just weren't possible before. That at the end of the day, that although building experiences is a very difficult thing, that it's the photorealistic content availability that is ultimately the limiting factor. And scaling that is very difficult, particularly when you think about all of the variation that exists out in the real world. And lastly, computer vision and machine learning, I believe together can enable computers to do what each of those technologies failed to do independently. And that I'm very excited about the fusion of them in order to go after this exciting problem. So, thank you very much.